I want you to look at the nearest window. Go ahead, look at it. It is transparent. It is hard. It holds back the wind and the rain. If you knocked on it, it would feel as solid as anything you have ever touched. And if you asked 100 people what state of matter glass is, every single one of them would say the same thing. Solid. Obviously solid. What else would it be? I am here to tell you that that answer is wrong. Not wrong in a technical, pedantic, fine print kind of way. Wrong in a way that changes what you think you are looking at. Glass is not a solid. It has never been a solid. The window you are looking through right now is, by the most precise definition physics has to offer, a liquid. An extraordinarily slow, extraordinarily viscous liquid that has been flowing continuously since the moment it was made. So slowly that you will never see it move in your lifetime, but moving nonetheless. The glass in your window is flowing right now. I have spent my career thinking about the fundamental structure of matter, about what distinguishes one phase from another at the deepest level. And glass kept coming back to me as one of the most instructive cases in all of physics. Not because it is exotic, because it sits on your windowsill, because you look through it every day without realizing that you are looking through something that physics has never fully agreed how to classify. Something that sits between states of matter in a way that reveals how the categories we use are simpler than the reality they describe. I am going to tell you what glass actually is, why it flows, why it is transparent, why it shatters instead of bending, and what all of that tells you about the nature of matter itself. By the end, you are not going to look at a window the same way again. Let us start with what we mean by solid and liquid, because the distinction is less obvious than it seems. When most people think of a solid, they think of something hard, rigid, and fixed in shape. When they think of a liquid, they think of something that flows, that takes the shape of its container, that you can pour. And these descriptions are not wrong, but they are descriptions of behavior, not of structure. And physics cares about structure. The real distinction between a solid and a liquid at the atomic level is not hardness or the ability to flow. It is order, specifically long-range crystalline order. In a true solid, in iron, in table salt, in diamond, in ice, the atoms are arranged in a precise, repeating crystal lattice. Every atom knows exactly where it is relative to every other atom. The pattern repeats perfectly across the entire material. Millions, billions of unit cells, all aligned, all regular, extending in every direction. That is what a solid is at its foundation. Not hardness, order. A liquid has no such order. The molecules in liquid water are constantly moving, bumping into each other, forming temporary connections and breaking them. There is local structure. A water molecule and its nearest neighbors form brief, fleeting arrangements, but no long-range order, no repeating pattern across the bulk of the material. Ask where any particular molecule is relative to one a centimeter away, and the answer is no predictable relationship. Liquid structure is local, temporary, and constantly changing. Now, when a liquid cools down and freezes into a solid, what actually happens? The molecules slow down. The thermal energy decreases. At a specific temperature, the freezing point, the molecules lose enough energy that they can no longer resist the attractive forces between them. They settle into the minimum energy configuration, which is the crystal lattice. The long-range order snaps into place. Suddenly, every molecule has a fixed position relative to every other molecule. The liquid has become a solid. This transition, the freezing point, is sharp. It happens at a specific temperature. Above that temperature, liquid. Below it, solid. The transition is what physicists call a first-order phase transition. There is a precise boundary, a definite moment when order appears. Glass never does this. When you make glass, you take a material, typically silicon dioxide, the same thing sand is made of, and you heat it until it melts into a liquid. Then you cool it. But you cool it fast enough that the molecules do not have time to find their way into the crystal lattice. They are moving more and more slowly, losing energy, getting more and more sluggish. But they never reach the moment where they snap into order. They just keep slowing down. The viscosity, the resistance to flow, increases enormously. But the structure never changes. It stays disordered. It stays liquid. What you end up with is a liquid so viscous, so resistant to flow, that it behaves in every practical sense like a solid. It holds its shape. It is rigid on any human timescale. But its atomic structure is still the structure of a liquid, random, disordered, no crystal lattice, no long-range order. The molecules are frozen in place not because they have found their equilibrium crystal positions, but because they have run out of energy to move while still stuck in a disordered arrangement. Physicists call this an amorphous solid, or a glass. The word glass, in physics, is not just the name of the stuff in your window. It is the name of an entire class of materials that share this property. Frozen disorder, liquid structure, solid behavior. And this distinction between a crystal and a glass is not subtle. If you took your window and put it under an X-ray diffractometer, the instrument that physicists use to study atomic structure, you would see something completely different from what you would see with a crystalline solid. A crystal produces sharp, precise diffraction peaks, spots of intensity at specific angles, revealing the regular spacing of the lattice. Glass produces a broad, diffuse halo, a smear, the signature of a material with no repeating order. The X-ray cannot find a pattern because there is no pattern to find. But wait, if glass is a liquid, why does it not flow? Why can you lean on a window without it slowly oozing downward? The answer is viscosity, and the range of viscosities in nature is one of the most extreme ranges of any physical quantity we measure. Water has a viscosity of about 1 millipascal second. That is the unit. Honey is about 10,000 times more viscous than water. Tar is about 1,000,000 times more viscous than water. Glass at room temperature is about 10 to the power of 23 times more viscous than water. That is 100 billion trillion times more viscous than water. That number is so large, it is almost meaningless. Let me try to give you a sense of it. If you took a block of room temperature glass and waited, it would flow. But the time it would take to flow by a measurable amount, to sag, to deform, to show any movement at all, is longer than the age of the universe, by a very large margin. The glass is flowing. The rate is simply so incomprehensibly slow that no human civilization could ever observe it directly. This is why the old myth about ancient window glass being thicker at the bottom, supposedly because the glass has flowed downward over centuries, is almost certainly wrong. Medieval glass is thicker at the bottom because of how it was made, not because it has flowed. At room temperature, the viscosity of glass is so extreme that even 1,000 years is nowhere near enough time to produce measurable flow. The glass has not moved. It is simply a liquid that moves too slowly to observe. But it is still a liquid. The structure is still disordered. The molecules are still in a liquid arrangement. They are just not going anywhere on any time scale that matters to us. Now I want to tell you about something called the glass transition, because this is where it gets genuinely strange. When you heat glass, it does not melt at a sharp, specific temperature the way ice melts. Instead, it gradually softens. As you raise the temperature, the viscosity decreases smoothly and continuously. The glass gets softer and more pliable. Glass blowers exploit this. They heat glass until it is soft enough to shape, blow into it, stretch it, form it. Then they let it cool, and it hardens again. All of this without any sharp phase transition, without any freezing point. The glass just gets more or less viscous depending on temperature. The temperature at which glass transitions from being hard and brittle to being soft and workable is called the glass transition temperature. For window glass, it is around 500 to 600 degrees Celsius. Below this temperature, the glass is hard and brittle. Above it, soft and pliable. But here is the thing. The glass transition temperature is not a true thermodynamic phase transition. It is not like the melting point of ice, which is sharp and well-defined and independent of how fast you heat or cool a material. The glass transition temperature depends on the cooling rate. Cool the glass faster, and the transition appears at a higher temperature. Cool it slower, and the transition is at a lower temperature. It is not a property of the material alone. It is a property of the material and the process. This drives theoretical physicists slightly mad. A phase transition that depends on the process? That is not supposed to happen. Phase transitions are supposed to be properties of equilibrium states, thermodynamic facts about the material. The melting point of water is 0 degrees Celsius, full stop. It does not matter how fast you cooled it. But the glass transition is not like that. It is a kinetic phenomenon, a consequence of the molecules running out of time to find their equilibrium configuration. The glass is, in a deep sense, not in equilibrium. It has never been in equilibrium. It is a material that is permanently, fundamentally, out of equilibrium with itself. Glass is frozen disorder, a liquid that never finished becoming a solid, a material caught perpetually in the act of trying to crystallize and never quite managing it. This raises a question that has occupied physicists for decades. Is the glass transition a true phase transition? Is there a real thermodynamic difference between the glass and the supercooled liquid above the glass transition temperature? Or is the glass just a very slow liquid with no fundamental distinction at any temperature? The honest answer is that we do not fully know. The glass transition is one of the genuinely open problems in condensed matter physics. We have good phenomenological descriptions. We can predict the viscosity as a function of temperature. We understand the basic mechanism, the molecules getting trapped in a disordered configuration. But a complete first principles theoretical understanding of the glass transition, derived from the underlying quantum mechanics of the atoms, does not yet exist. For someone like me, who spent a career looking for the deep mathematical structure underneath physical phenomena, this is both frustrating and exciting. Frustrating because the answer is not yet there. Exciting because that means it is still waiting to be found. Now let me tell you why glass is transparent. Because this is a separate question from why it is amorphous, and the answer involves quantum mechanics in a way that I think is beautiful. Most materials are opaque. Metals, wood, stone, ceramics. You cannot see through them. Light hits them and is absorbed or reflected. It does not pass through. Why not? The answer involves the quantum mechanical structure of electrons in the material. Electrons in a solid do not have continuous energies. They are confined to specific energy levels, organized into what physicists call bands. There is a valence band, the energies where electrons normally live, and a conduction band above it, the energies electrons move into when they conduct electricity. Between them is a gap, the band gap, a range of energies that electrons simply cannot have in that material. When a photon of light hits a material, it can be absorbed if it has enough energy to kick an electron from the valence band up into the conduction band. If the photon's energy is greater than the band gap, it gets absorbed. If it is less than the band gap, the electron cannot absorb it. There is nowhere for the electron to go, and the photon passes through. In metals, there is no band gap. Electrons can absorb photons of almost any energy. That is why metals are opaque and shiny. They absorb and reflect light across a wide range of energies. In silicon dioxide, the main component of glass, the band gap is large, about 9 electron volts. The photons of visible light, which range from about 1.8 to 3 electron volts, do not have enough energy to cross the band gap. They cannot be absorbed. They pass straight through. Glass is transparent because its electrons are not allowed to absorb visible light. The quantum mechanical rules of the material simply forbid it. And notice that this transparency has nothing to do with whether glass is crystalline or amorphous. Pure crystalline silicon dioxide, quartz, is also transparent. The transparency comes from the band gap, which is a property of the chemical bonds between silicon and oxygen, not of the long-range order. The disorder of the glass structure does not destroy the transparency, because transparency is a local quantum mechanical property, not a structural one. Now, why does glass shatter? This is the other thing everyone knows about glass. It is brittle. Hit it hard enough and it does not bend, does not dent, does not deform plastically the way metal does. It shatters. Clean breaks, sharp edges, explosive failure. In a metal, when you apply stress, the crystal lattice can deform. Planes of atoms can slip past each other. The material yields, bends, changes shape without breaking. This is called plastic deformation. And it is possible in metals because their crystal structure allows atomic planes to slide. The metal is tough precisely because it can redistribute stress by deforming. Glass cannot do this because glass has no crystal structure, no planes of atoms, no organized lattice that can slip. The disordered network of silicon and oxygen is rigid and interlocked in a random way, with no preferred directions, no planes of weakness along which deformation can propagate. When stress is applied, there is no mechanism for gradual deformation. The stress concentrates at tiny flaws, microscopic scratches, inclusions, surface defects, and at those points the concentration of stress becomes extreme. The bonds at the tip of the flaw break, the crack propagates, and because glass cannot redistribute the stress by deforming, the crack runs all the way through the material almost instantaneously. Glass shatters because it is too disordered to deform. The randomness that makes it a liquid is the same randomness that makes it brittle. The structure that has no crystal order has no way to absorb and redistribute the energy of a blow. There is a deep irony in that. The disorder of glass, the thing that makes it technically a liquid, is also what gives it its characteristic failure mode as a solid. The amorphous structure causes both the slow flow and the sudden shattering. Two completely opposite behaviors, both consequences of the same underlying lack of order. And then there is one more thing I want to tell you. Something about glass that connects it to the deepest questions in physics. Something about what it means for matter to be in equilibrium. Glass is a non-equilibrium material. I said this earlier, but I want to dwell on it. When silicon dioxide cools from a melt, the equilibrium state, the state with the lowest free energy, is crystalline quartz. That is where the material wants to be, thermodynamically. That is the arrangement of atoms that minimizes the energy. Glass is not in that state. It is in a higher energy, disordered state, trapped there by the kinetics of cooling. Given infinite time, glass would crystallize. It would find its way to the equilibrium configuration. It just needs time. A lot of time. More time than the universe has existed. But thermodynamically, it is always trying, always moving, however imperceptibly, toward the crystalline state it never reached. Your window is trying to become quartz. It has been trying since the moment it was made. It will be trying long after every human being alive today is gone. It will never succeed, but it will never stop trying. That, to me, is one of the most extraordinary things about glass. Not that it is a liquid, not that it is transparent, but that it is a material permanently stranded between what it is and what it wants to be, frozen in a state of perpetual, imperceptible becoming. Physics is full of these cases. Cases where the difference between what a material is and what it wants to be is hidden, invisible, imperceptible on any human timescale, but real and important at the level of fundamental theory. The ground beneath your feet is riddled with such cases, materials in metastable states, systems that have not found their equilibrium and may not for billions of years. The universe is full of things that are, in the most precise thermodynamic sense, not quite finished yet. Glass is simply one of the most elegant examples. One you can hold in your hand, one you can see through, one that has been sitting on the windowsills of human civilization for thousands of years, quietly, invisibly, being more interesting than anyone looking through it ever suspected. When I think about what glass teaches us, I keep coming back to the same lesson that quarks teach, that water teaches, that every deep physical investigation teaches eventually. The categories we use in everyday life, solid, liquid, ordered, disordered, are approximations, useful ones, necessary ones. You cannot live without categories. But they are not the territory. They are the map. The territory is stranger. The territory is a material that is simultaneously a liquid and a solid, depending on what question you ask and what time scale you consider. A material that has a structure indistinguishable from a liquid, but behavior indistinguishable from a solid. A material that is transparent because of quantum mechanics, and brittle because of disorder, and flowing because of thermodynamics. All at once. All the same material. All the same window. The next time you look through a window, remember what you are actually looking through. A liquid that has not moved in your lifetime. A material trying to crystallize on a time scale longer than the age of the universe. A quantum mechanical filter that passes exactly the light your eyes can see and blocks the rest. A brittle, frozen, flowing, transparent, disordered, non-equilibrium, almost solid that does not fit cleanly into any of the categories you were taught. Glass is not what you think it is. It never was. And the window between you and the outside world has been quietly proving that every single day for as long as windows have existed. We just were not asking the right questions.